I'll introduce FruitNinja, our method for generating realistic internal textures in 3D objects with Gaussian splatting. I'll show how it enables real-time slicing and rendering under any geometric transformations. In the real world, objects often contain intricate internal textures that are revealed when sliced. However, current 3D modeling techniques, such as neural radiance fields and 3D Gaussian splatting, are trained primarily on external views. These methods capture only surface appearance and ignore internal structures. As a result, when geometric transformations expose interior regions, the models often produce significant artifacts that break realism and visual coherence. Now let's look at the challenges of this problem. First, training data for object interiors is extremely rare. Capturing internal textures typically requires slicing or destructive scanning, which is difficult and often infeasible. As a result, most existing 3D datasets, such as ShapeNet, CO3D, and OmniObject 3D, only contain exterior views. Second, there are infinite possible slice angles. Unlike external views, which are limited and predictable, the interior can be revealed from any direction, making exhaustive supervision infeasible. Since 3D interior data is unavailable, one strategy is to rely on 2D sliced views for supervision. But this introduces a third challenge: maintaining consistency across slices. Cross-sectional slices may contain conflicting signals. For example, one slice might show a seed while another shows only red flesh in the same region. This ambiguity makes it difficult to infer a globally coherent and realistic interior in 3D. Since 3D interior supervision is rarely available, generative methods are the only practical solution for this task. Generating arbitrary interior slices is under-constrained and difficult to supervise. Instead, we introduce a few user-defined cross-sections along canonical planes, such as XY, YZ, and XZ. These views are easier to obtain and serve as effective anchors for training. We use them to guide the generation of realistic internal textures via 2D supervision. The first step of our method is internal filling. We discretize the 3D space into a voxel grid and shoot rays along 6-axis aligned directions. Using a ray collision algorithm, we place new Gaussians at intersections with the object's volume. This populates the interior with structure-aware particles and provides a foundation for texture generation. Then, we generate an initial set of pseudo-ground truth views using stable diffusion at the user-defined slicing angles. After these slices are trained, we render the same cross-sections and optimize them using a 2D diffusion model with SDS loss, while applying 3D voxel smoothing recurrently. In each voxel, we assign colors to untrained Gaussians by averaging nearby trained ones using inverse distance weighting. It solves two issues: filling in untrained regions that weren't covered by slice supervision, and improving local texture consistency by propagating color patterns across 3D space. Additionally, we propose opaque atomic Gaussians as part of the training pipeline, specifically designed for the real-time slicing setting. This formulation enhances learning stability and preserves sharp color transitions at material boundaries. Interior Gaussians are assigned uniformly high opacity, and atomic clipping is applied to prevent oversized particles. With all components integrated, our pipeline produces 3D models with consistent internal textures and supports slicing at arbitrary angles. This is demonstrated by slicing the object along a fixed path, revealing internal Gaussians that were not explicitly optimized. Our method outperforms existing approaches such as Phys Gaussian, which initialize internal Gaussians using nearby surface properties. Thank you for watching.